Welcome back, my statics friends. In this video we're going to continue our investigation of equilibrium and how to apply the equations that we showed you in our last video to problems in 3D. So without further ado, let's get started. In statics, 3D equilibrium problems are often some of the longest hand calculations that you'll encounter, and part of that is just the nature of the math that's involved. They're not overly difficult, and in fact, the basic steps you see will be very similar to what we did in our last video with finding equilibrium in 2 dimensions. The only problem is now we have to make vectors out of everything, and just by its very nature, when we do our moment, a cross product of vector is a long operation. But it's not hard, and if you look at it piece by piece, it's pretty straightforward, and I'm going to show you kind of how to do that. We've got an example that we're going to take a look at when we do it. So just kind of generically thinking here, let's take a look at what the requirements are. For equilibrium in 3 dimensions, just like we had before, we had to have a translational equilibrium requirement as well as a rotational equilibrium, and they're accomplished in the exact same way. The first one is I do sum of forces. And well, remember, if this is a vector, the sum of a force vector of a series of force vectors, that's a resultant, and a resultant in this case for equilibrium, we're going to force it to 0. Okay, and then for the moment, for rotational equilibrium, it's the same thing. We're going to take the moment of everything on the object, call that as a moment resultant, and now we're going to put the additional constraint of 0, and that's what makes it an equilibrium problem. So it's the exact same thing we did back in chapter 3 and chapter 2 when we were finding resultants of forces and equivalence of forces and all that, except now we're going to prescribe those resultants to be a certain value, and it's this 0 that is the equilibrium that we're looking at. So if we look kind of as we set this problem up, I'm going to show you kind of generically, here's my object in space, and it has a whole lot of forces acting on it. Now again, this doesn't represent a real physical object, but it is a conceptual model of what you might encounter. So I've got my object here has a point A, which is subjected to a reactionary force that is made up of an X component, a Y component, and a Z component. Okay, there is no moment at A, so this is actually a ball and socket joint. And if you recall a ball and socket from our free body diagram video in 3 dimensions, it's basically a 3-dimensional pin, right, in which I have 3 forces, an Rx, that says F, that's an Rx, an Ry, and an Rz acting at a point, and then that there is no moment at that point. Okay, so it's all a matter of getting our support condition considered. So that's what we're saying is happening here. Now, on the picture, I didn't draw the moment because they were all 0, so we're not worried about what its effect is on the object. All right, so if we take a look at it, so that's our support reaction here. Okay. All right, now we also have 3 points with forces and moments acting on them as well. At point 1, I have a force vector F1 and a moment M1. At F2, I have a force vector F2 happening here and a moment vector M at 2. Now again, these could be positive, negatives, they could have I's, J's, and K's. They could be any sign, they could be 0, it could be anything. Again, this is just a very general layout of it. All right, and then the same thing up here at 3. I have a force at 3 and a moment at 3. And again, they're all kind of going in different directions. Again, we're not too worried about what's going on there. Let's see, we got a little bit of a focus issue. Let's see if I can clean this up a little bit. There we go, that's better. Okay, all right, so that's my general free body diagram. And so all we're going to do then is for any free body diagram that we generate is we're going to write our equations for the forces and for the moments. Okay, so we're going to apply those equations to that picture. So the first one we do is always, is a force equation, and it's pretty straightforward. All we're doing is finding the resultants of just the forces. And if I do that, all I have on this is an F1, an F2, an F3, and Ra. Okay, the moments don't add into this equation because this is a force equation. This is the translational requirement, and the moments don't affect that. So all I'm doing is I'm writing my equation, and that's F1 vector plus F2 vector plus F3 vector plus my reaction at A vector is all equal to 0. Okay, Now again, this guy we could have written as ax vector plus ay plus az, and I may or may not know these values, but for now, I'm just writing the equation, and then we'll come in and figure out what do we know, what don't we know, and go from there on our approach. But the vector form, you should be able to do this on any statics problem. Okay, now the second equation that we looked at, we said was our moment resultant equation. Now, the moment is one of the most powerful equations in all of statics, and that you get to choose the point at which you want to take it. For the purposes of this exercise, I'm going to take it about the origin, but it doesn't matter. The point that you choose for equilibrium to exist has to be 0 at all points. Okay, it could have easily been a point on the, on the object. It could have been, 0.3. It could have been anywhere. And there will be strategies that we'll talk about in the videos and the techniques coming up that will help you choose what your point is. But for the sake of our argument, I'm going to take it as O. A lot of times we take those, at a support condition that has a lot of unknowns, because if I take a moment there, this guy doesn't contribute to the moment. But for this one, again, I want to make sure that he stays in the equation, so I'm going to take it about O, and we're just going to look at what the formulas are doing for us. Okay, and so the general formula for that then, if you remember, moments are always some R cross F. Okay, I need a position vector, and I need a force vector. And so what I have is, let's take a look, and we'll go through and do each of the force vectors one by one. So what I have then is, in order to get a moment at O, I like to write things with a subscript. That if I do a moment vector equals some R vector crossed into an F vector. Okay, let's say that this is acting at, a point M. Okay, and I want to be looking for a moment taken at point, for lack of a better idea, say L. Okay, the way that I know what position vector I need is I take these two subscripts and I write them in the same order. All right, so my position vector would be from L to M, and that way these two pair up and those two pair up, and that's the pairing that I need. And this is important because this determines the direction of the vector. All right, so let's try that with F1 down here. So F1, I want the moment at O here, okay, and I want the moment that the F1 force causes about that point. So we're going to do a cross product. Here's my R cross F. And so if I use that same idea that we just did here, it's an R from O, so those two match, 2.1, those two match. And that's exactly what we're going to do. And if I look down below, that would be something that kind of looks like this. That again, I just look at only the one force that I'm interested in. The rest of the object doesn't matter. The shape of the object doesn't matter. The other forces don't matter. I'm doing them one by one as I move through the system. So here's my F1 from my picture, and here's my O, and that's 0.1, and here's the position vector. It goes from O to 1. And so you can construct this. Presumably you know the coordinates of O and you know the coordinates of 1. You can find this position vector. If you don't remember how to do that, go back and look at the vector on creating position vectors, and we'll show you how to do that, the video on position vectors, I should say. Okay, so that's what we're looking at doing, and we just basically repeat that process for everything else. So now we go to the second one, and for the force at 2, I need an R from O to 2. Okay, and so if I look at that, then same object, my F2 now on that picture was acting kind of downward. Again, I don't care about the signs. These are just vector equations. It's one of the beauties of working with vectors. All right, and so then R from O to 2 goes from O up to 0.2. That would be this point here, and that's the vector. And so again, if you know the coordinates of 2 and the coordinates of O, you can find that position vector. And that gets me that one. And then same thing for 3. I need an O, and I have a force at 3. I need a vector from O to 3. Now, if you recall in our force vector, or in our moment vector calculations, we said that all I needed was a point somewhere on the line of the force. Okay, I just happened to choose the one where the force was acting, but it could have easily been, a point down here or a point there, whatever makes the math easier, because the cross product operator will fix all that. But I'm going to the specific point of application, but you don't necessarily need to do that. Okay, so RO3 crossed into F3, got it. And then the other piece that's on here that hadn't been included before is I also have these concentrated moment vectors. Get some hats on here. That needs a hat. And M2 does have a hat. Okay, so those are vectors. And so for those, remember, moments are free vectors. So they already have the units that you want. They're already moments, and we just add them explicitly to the object. So all I'm going to do is add M1, add M2, add M3, and this whole thing, and it's a bit of a long equation, is all going to be equal to 0. Okay? And then, I'm missing one. Can you tell which one I'm missing? I'm missing RA. So there should be an R from A to A, from O to A. Find my eraser here real quick. Got ahead of myself. Okay, R from O to A crossed into an FA vector. Okay, and again, I need an O, I have an A, this should be OA. And so that picture then is here. So from O to A, there's my reaction vector. Okay, and then this is the position vector that I would need to produce R from O to A. And then of course I add M1, M2, and M3. Those are my the free moments. Okay, so then once you have all of that figured out, now you can go in and you can actually build the 3x3 determinants. And this is where the math gets long and ugly. Okay, so again, all we're going to do is for each one of these pictures that I drew up above that has a cross product, this is the cross product operator. I'm going to do an IJK, and then my RO1 will have an X piece and a Y piece and a Z piece. Those are the guys that go here. So X goes under I, Y goes under J, Z goes under K. Okay, and then the force vector also has an X, a Y, and a Z component. And that's what we're going to put there is the pieces of F1 that come out of F1X, F1Y, F1Z, so forth and so on. And I basically repeat that process all the way through all of these cross products. Okay, now a lot of times in this, we've written this equation as if I didn't know any of the values. Now at this point, you can go in and start picking out what do I know. Usually position vectors you know. A lot of times applied forces you know. Often supports you don't. So if you don't know it, you just keep the math operator here and keep them as variables, AX, AY, AZ, okay? And compute what you can. Sometimes you don't know where a force is applied, but you're looking to find out where it needs to be to cause equilibrium. Maybe you don't know the R's. This would be that equivalence calculation that we did a couple of videos back. So again, if you need to review, go back and take a look at that. But that's the process that we're looking at as we apply to it. And again, don't forget M1, M2, and M3 here. All right, so let's give one a try. Okay, and kind of my friendly note was if you don't know a particular value, keep it as an unknown variable in the equation. That's kind of our recommendation here. All right, so let's try one, put some numbers on it, and that way you can kind of see where things are coming from, and we'll show you the whole process. All right, this is a fairly straightforward three-dimensional object, but it could be anything. What I have is I have an object that is fixed to the wall. Okay, it has a moment at B applied. Okay, that's my double-headed arrow. And again, I don't really care, when I do it with vectors, I don't care the orientation that the arrow is in the right directions because my vectors are all going to be written with positive and negatives on the ij's and k's that will tell me those directions when I solve them. And then, and so I have a point A at the wall, B is where the moment is, and then it has this three-dimensional elbow bend, and then out on the end of this lever arm at point E, I have a force vector E that is 100 newtons I plus 150 newtons J minus 200 newtons K. Okay, and then the moment at B we're going to be given is minus 50I plus 25J minus 15K. Okay, and the units on that are Newton meters, and that will be the moment that's here. Again, I'm not worried about the picture. I need the picture to get the vector on there, but I'm not worried is it up and to the left or is it down and to the right? Is it over into quadrant 7? I don't care about that. We just need a picture representation. Okay, so that would be our basic before picture, if you will. What we want to find is the support reactions that make up this connection at the wall. So I need to know if it's a fixed connection, I know that there's an RA and an MA at the wall. And we want to find out what their values are and how we're going to solve those. Okay, now, if you remember from our 3D discussion, a fixed support, in 2 dimensions had, look something kind of like this. That we had a moment, we had a Y, and we had an X associated with that was in 2D. Okay, in 3D, now you have all three. I have a force in the X, a force in the Y, and a force in the Z. I don't know their values at this point, but we'll find them. Okay, and then the moment this was a moment about a Z-axis in 2D. Well, now I have a moment about an X-axis, a Y-axis, and a Z-axis. But again, we can write all of these as vectors, so they're just vector sums. So I can take that big vector and split them into little pieces. And that will be one of the tricks that we'll have to do in order to be able to solve this. So we'll be dealing with, while we're mandating that the resultant effect is 0, we're going to be taking these unknowns and splitting them back into components that are Cartesian on a lot of the vectors that we do. And that's a very common practice. All right, so let's draw our free body diagram. You can see it's a whole lot simpler. I didn't even draw the dimensions. We'll copy those down if we need them. All right, and so if I look at it, my free body diagram then is that at A, I have a moment vector, and that's the double-headed arrow, and an RA vector acting at A. Okay, at B, I had my moment, so that's a double arrow. Okay, and at E, I have my FE. That's our free body diagram. Again, I do need the dimensions, so we'll include those, but for just the sake of keeping the picture clean, I'm not writing them down, but it's just we're going to copy that information down. All right, so that's my valid free body diagram of the whole system. That's always step number 1. always step number 2 is write the equations for the picture that you just drew. Okay, now we may do this in multiple iterations, refine our free body diagram or start cutting things in future free body diagrams, but as always, draw a free body diagram, write the equations. Draw the free body diagram, write the equations. It starts sounding like a broken record. Okay, if in doubt, draw a free body diagram and write an equation and see what you can find. All right, so the first thing we do is we're going to write the forces equation, the resultant of the forces. Okay, and so for the picture that we just drew, again, I'm not worried about what's happening up above. I'm just looking at what's happening here. The only forces on this system are the force at A and this force at E. So my equation is RA plus FE, and all that better be equal to a zero vector. That was the definition of translational equilibrium. All right, so now I can take in and I can plug in my pieces. My RA, let's go ahead and move in AX, AY, and AZ. That was his components. Okay, and all of that's going to be equal to a negative FE vector. Now what I've done is I've taken the FE and I've moved it over to the other side, and now I have an equality that relates these. Okay, and we know that FE was 100 newtons plus 150 newtons minus 200 newtons, and we've flipped the sign on it by moving it to the other side, so that's why this minus sign is out in front. And if I do the math, it is now minus 100 newton I minus 150 newton J plus 200 newtons K is the value of my reaction at A. And again, this guy is our A. Okay, and then if I substitute in, that's where I got that piece. So now I can look at, well, this guy is clearly an I vector, this is a J vector, and this is a K vector, which means then that this guy has to equal the I part, and this one has to equal the J, and this one has to equal the K. All right, so I can come in and say that my AX vector is minus 100 newton I. Okay, my AY vector is minus 150 newtons J, and my AZ vector is minus 200 newtons K, and that's how we get those. Now, if you remember that any vector V can be expressed as its magnitude dotted into a unit vector, then in the X direction, I know that my unit vector was positive I. The magnitude of that vector would be minus 100 newtons. Okay, and basically that tells me that this component is acting in the opposite direction of positive X. So instead of acting down the line, and again, this is X positive here, okay, he's actually pulling away. And that should make sense. If this guy is pulling in the X direction, I need this one to be holding it back in the opposite. So that's why we got a negative sign on that. So that jives with what we're thinking. AY is minus 150 newtons J. Again, I just took this one, and the only one that it pairs up with is the J. Okay, and so my AY then is minus 150 newtons. Again, the minus tells me it's opposite of positive Y. Okay, now again, where we got to be careful, back in the scalar forms of this, we always said if you got a negative sign, it indicates that it's opposite of what you drew on the picture. Well, I didn't draw really anything in the proper direction on the picture. I just assumed that it's going to follow a positive sign convention. And so the negatives on that will fix itself. That's one thing that we can do with vectors. It's one of the things that's nice about vectors is they will self-correct, and I don't have to be careful with the positive and negatives. It will work itself out in the math. Okay, so I know we're kind of violating our statement that magnitudes are always positive, but we're going to keep the signs on this and no negatives here as an indicator that it is opposite of what we assume to be positive. All right, and then AZ is the last one. AZ has to be the 200, and that should be... that is a positive 200. I have, yeah, and so on that one, and so that's a positive 200 newtons there, and then the positive tells me that it's pointed towards Z for that. So you've got now the reaction forces, AX, AY, and AZ. Okay, the next step then is to go do the moments. So for this problem, again, often we look for places where the most unknowns are, okay, and at the beginning of the problem, the most unknowns were clearly at A. And one reason that I would choose the sum moment today is if we made a mistake in our calculations in the first part, say we had a math error, by summing moments here, I eliminate that from causing a problem in any future calculations. Okay, now sometimes you can't avoid having to reuse a calculation, but this is a chance to at least get the moment right, even if I screwed up the force vectors. Okay, so that's why I'm choosing to go to A, and that's often a trick is you sum moments at a support condition. Okay, that has a lot of unknowns because you just don't want to deal with them or have to worry that you've done something wrong in your calculations. I mean, I know there's such a thing as having confidence, but let's be realistic. It's easy to make a mistake. You saw me make a sign error here. Just, it's very easy to do. So again, that's why I would choose to go to find the moment resultants. Okay, so we're going to do a moment resultant is the sum of the moments on the object, all equal to 0, and we're going to choose point A. And so now, again, all we're going to do is we're going to write that equation like we did in the more general example, that I need all the forces get R cross F. So my force reaction at A is at A, right? So I'm going to do a position vector from A to get me what would be a moment vector at A, and this whole thing we said has to be equal to 0. So again, force at A, moment at A, R is from A to A. Well, we know that guy is 0. The start and the end point are exactly the same. So this first term doesn't matter, and that's why we chose that point, was to force this to be a 0 value so that this guy wouldn't have an impact on the calculations. The other piece of it then is that we have R from A to E, is force at E, and I want a moment at A, so we need the position vector from A to E. Okay, and again, I'm not worried about what it actually is at this point. We're just writing the basic vector equation. And then that's the only two forces I had were RA and FE. I also need to add in those free moments that are on there. And I'll get the applied moment MB and the unknown reaction moment MA happening here. And so those just get added into the equation. And we know that this whole sum has to be equal to 0. Okay, so if I accept that this term is 0, it goes away. This is the last piece of it. So now we can go in and we can start to solve for this. Okay, so things that we know. Okay, reaction at A is an AX vector plus an AY vector plus an AZ vector. The AX vector is magnitude of AX times I plus a magnitude of AY times J plus a magnitude of AZ times K. Again, we've assumed a positive direction. And again, this is unknown at the time we started the problem, as is the moment. The moment at A then is a moment vector about the x-axis plus a moment vector about the y-axis plus a moment vector about the z-axis. And again, this is unknown. Or something kind of like that. So we can take the magnitude of the moment times a positive I, magnitude of the y times a positive j, and magnitude of the z times a positive z. And I can get these back into, so I can go from vectors to magnitudes as we start to kind of look at this. All right, so let's plug in the parts to our basic equation. So if I drop this guy back up here, we're going to fill in what do we know about this equation. All right, so I've actually kept the RA, A and RA in here, and we can come up with the pieces that we can look at. So the first term is IJK, and my R from A to A is 0, 0, 0. That's what made this whole thing equal 0. Okay, I had an unknown AX, an unknown AY, and an unknown AZ that would have showed up there. Okay, but again, that whole thing is 0. The second term is R from A to E crossed into FE. Okay, so if we look at what it takes to get to from A to E, again, we're assuming positive Z is this way, X is here, and then, of course, positive Y is here. That's the exact same coordinate system we had in the original picture. Okay, so if I need a position vector that goes from A to E, my tail is here, my head is here, the path that I have to walk to get there is I go down this direction 5 meters in the X direction, I go up 2 meters in the Y direction, and I go over 1 meter in the negative Z direction. It's behind, because positive Z is on this side of X, and this guy is going back the opposite. Again, I know the picture is not real clear, but I'm just saying that was my intent in this problem. Okay, so if we look at that, then my position vector from A to E is +5, +2, -1. Okay, and so we've got that. The force vector at E we were given, and that was +100, +150, -200. That's the force at E, and then of course IJK in the first row. So that's the 3x3 determinant that computes that moment. Okay, and then we have plus MB, that was a given, -50I, +125J, -1, did I do 15K? I said 15, I wrote it as 15 all the way through here, didn't I? Okay, this should be a 75, so we're going to have to make some math corrections on the original picture. Not that it really matters, but let's just do it right to the way that it was drawn. All right, so that becomes a -75. This one up here is a -75 on that one. Okay, let's see, got it. And there will be one other place that we'll have to correct it down below. Okay, so all I've done is I've evaluated the math of the determinant. So I take my I vector, that's +2 times -200, minus a -1 times 150. So that's the 2x2 evaluation, and that's multiplied by I. Okay, I do the J, it's a 2x2 of 5 times -200 minus a -1 times 100, but it gets a minus in front, so don't forget that minus there on this. You can also do Saros's rule on this, where we circle the diagonals and do it this way. I'm just doing it just by the formulas. Okay, and then we've got our last one for K is I eliminate the rows and the columns, and I have 5 times 150 minus 2 times 100. That's this guy here. And then, of course, I copied everything else down on here. Now again, we haven't solved for MA. MA is unknown. Okay. All right. So if we go through and we simplify this whole thing becomes a minus 250 newton meters I plus 900 newton meters J plus 550 newton meters K. That's the evaluation of that moment. I'm just copying these guys down again, repeating the lines, and then we'll go simplify. Okay, and so this is where I now start collecting terms. So I've got an I term, a J term, and a K term, and I start combining everything into it. So the stuff with the I is a minus 250, minus 50, and the unknown MAX. It's the X component of this guy. Again, we went back and we pulled this equation in, knowing that MA was that bottom equation. All right, so that's my first equation. Okay. Okay, so we're going to call this little quantity as number 1. Okay, and then we know all of this is being equal to a 0 vector. Okay, so we'll take advantage of that. Okay, let's go do J. J was 900 newton meters. Okay, plus 125 plus MAY all times J is the second equation. And the third one, this is the one that I have to go make this a minus 75 on that. Okay. Now again, like I say, you see the problem where if I make a mistake early on, having to go back and correct it, I had to change 3 locations on this. Okay. All right. So, but again, just demonstrating an example. I meant to do that, right? Okay. So my K values are plus 550, minus 75. So that is another one. So this is the 4th location. Okay. Times K plus the moment about Z. Okay. And all of that has to be equal to 0. So that means that, you know, by saying this is a 0 vector, this is 0I plus 0J plus 0K is what that is saying. Okay, so everything in front of the I has to sum to 0. And so that's my first equation. I take what's happening in this equation, minus 250 minus 50, okay, is minus 300 plus MAX. MAX is now positive 300. So the moment is a positive moment about the x-axis. Okay, in this case, it's a torque. It's twisting that bar. Okay, in problem 2, we're now doing 900 plus 125. Okay, that's 1025 of newton meters plus MAY equal to 0. So MAY in this is going to be equal to a negative 1025 newton meters. Again, we're solving for MAY. Okay, and then MAZ is, now this is the one that changed a little bit. Instead of being 535, we're going to change that number to be plus 475. That's just the math that was inside of here. Okay, and then this number is going to change as well. Okay, and so plus 475 newton meters plus MAZ equals 0. This guy is a minus 475 newton meters. And that's all there is to it. It's long. The math is long, but it's not hard. Okay, and the hardest part is getting it to here. You know, getting these basic statics equations set up, and then from here on, we just go ask our mathematics friends, you know, your local neighborhood, you know, calculus professor, you know, hey, can you solve this for me? Don't do that. But just in general, it's, you know, the math isn't hard. It's a little cumbersome, and it's easy to make a sign error. And I'm, even to this day, after doing this for 20 some odd years, I still will drop a sign every once in a while. So you got to be very careful, and you got to be looking at the answers. Do they make sense to what's happening on this? Okay, and I can kind of check the moments on that as well. Okay, so anyway, that's what we have. I hope that's made sense to you. That's kind of our demonstration of 3-dimensional equilibrium. It's no different than what you did in 2 dimensions. Okay, we're just now doing it exclusively with vectors, and the math just gets a whole lot longer. So the moral of the story in this is that if you have a free body diagram and you don't know something like a tension in a rope, or I don't know a support reaction, put the vector on the picture, put it in the equations, and then when we get down in here, just leave it as an empty value. Okay, and that's what we did, and that's how I demonstrated how we found MAX and MAY, you know, up here for the MA vectors. And that's all there is to it. So let me know if this helped you out. If you've got any questions, leave some feedback down in the comments down below, and I'll happily answer that. Otherwise, be sure to like the video if you found it useful, and subscribe to our channel, and we will see you guys next time. Happy engineering.